Hello, dear students. Today we're going to talk about analysis of the relationship between the parameters of statistical aggregates. Today we're going to speak about correlation. Correlation is a value that describes the strength of an association between two variables. You might have heard of it because this term is frequently used not only in statistical context, but also in other way when two instances are somehow interrelated. But today we're going to speak about correlation coefficient. You might have heard of Pearson's correlation coefficient, Spearman's correlation coefficient, and Kendall's correlation coefficient. They are pretty similar one among with another, but today we're going to concentrate on first two. So the correlation coefficient for parametrical data, Pearson's correlation coefficient, and for non-parametrical data, Spearman's correlation coefficient. So let's begin with the top of an iceberg. What is correlation coefficient? How do we see it? How do we interpret it? So correlation is the term which describes the strength. It is very important, the strength of relation between two variables. Yes, so imagine that we point on the x-axis the body weight, on y-axis body height, and generally we expect that with the increase of body weight, with increase of body height, body weight will also increase. Yes, so it will be a positive correlation. If we imagine different kind of correlation, like can't come up with an example now, but with the increase of one parameter, another one will decrease. So this will be a negative correlation. Yeah, while with the increase of values on the x-axis, y-axis values will decrease, and there might be the example of no correlation. Yeah, while this is an example when kind of increase in one value does not result in any increase or decrease in other examples. So this is how, in general, correlation may look like: positive, negative, or no correlation. So you may, for your information, correlation coefficient is a value which limits are 1 and -1. So it can range from the highest possible value of correlation coefficient is +1 or 1 in this case, but you can also specify it as +1. And the lowest possible value for correlation coefficient is -1. Yes, so it can never be more than 1, and it can never be less than 1. If it is 1, it means that for all observations in our data set, if we plot these observations on a scatter plot, we can put through them a direct line which will go through the center of all points. Yeah, if this is the case, the correlation coefficient is 1. Yes, so with increase in one parameter, the other one is increasing as well, and it is the perfect fit. Yes, so with increase in one parameter by 1, the another one is increased by 1 or by 2 or whatever, but it is regular, pretty predictable, and straight line explains this dependency perfectly. If the dependency is reversed but still is very strict and predictable, it will be -1. Yes, so with increase of value on x-axis by 1, you see the decrease by 1 on y-axis or by another coefficient. This will be a negative correlation, and it will be -1. Yes, so still when the straight line goes through the points on the scatter plot for our data. Which caveat would I like to explain at this point is that correlation tells us only about the strength of relationship between two variables. Yeah, so if you can draw a straight line through the dots, it will be correlation coefficient of 1. and it doesn't count on the slope of the curve. Yes, so you can see the slope of the curve like this has a correlation coefficient of 1, and the slope of a curve which is kind of less steep, but still which resembles the first one by the position of all the dots on the straight line, still will have the correlation coefficient of 1. So what matters is the distance between the straight line, which describes the trend of the data. So closeness of this point or distance from this point to a straight line, they define the strength of the relation, but not the slope. The slope might be very minimal and still R will be equal to 1 because the points would be close or on the straight line. So not the slope, but the distance from the points till the trend line that defines the correlation coefficient. For example, here on example, you can see that if the points are a bit more distance from the straight line, correlation coefficient becomes a bit smaller, in this case 0.95. Yes, so pretty close to 1, but not the perfect fit. If these dots would be even farther from the straight line, the correlation coefficient will become even less, closer to the zero. Okay. And this is the case when correlation coefficient equals 0, when there is absolutely no correlation. So by increase in x value on the x-axis, you can tell absolutely nothing about what's going to happen on y value. For example, here you can see that for the value of x of 1, y will be equal to 2. Then you increase x by 1 each time, and y value goes from up to down in a regular way. So this dependency will be described as a straight line. So no correlation. You have no idea what's happening with the y value x with the value on y-axis when you control for the value on x value. So 0 correlation coefficient. How do we classify correlation coefficient? So we've said earlier that it can vary from +1 to -1. And roughly we can divide it into 3 categories. If it stands from 0 to plus or minus 0.29, this correlation will be called as weak. So very weak dependency between the values. If this correlation coefficient from 0.3 to 0.69 or minus 0.3 to minus 0.69, this correlation will be called moderate. And if it is closer to the value of 1, so above 0.7 and to 1, or below 0, minus 0.7 to -1, this correlation will be called as strong. So this was the basic information that you need to understand the correlation, how to interpret it, and what information can you get when you see that correlation coefficient is 0.5 or whatever. So for basic understanding, this is enough. But since we are on the lesson of statistics, we would like to look a bit under the hood of this process. So this is why we'll try to dig a bit deeper. So let's imagine that you have a data set. It doesn't matter what really we have measured, but we have the value of x, which has values of 1, 2, 3, 4, and 5, and we have a value of y or y, which has this number of value. We plot it on a scatter plot, and we can see that there is some dependency. So generally, with the increase of x value, y value increases as well. But we cannot be exactly sure. For example, if we get the value of 6 of x, we cannot be exactly sure where value of y will be or value of y will be. So we can expect that somewhere here, yeah. But to which extent can we be sure? To this question, the answer to this question can be gotten. We can get the answer to this question through the calculation of correlation coefficient. So before we begin with this calculation, I would like to say that thankfully, it's very good news. We have computers which can do all this work, which requires the patience and attention and time very quickly. For example, here you can see the simple script that you can write in the R environment. which will calculate you in a heartbeat all that you need to know about the correlation between these two values. So if someone is interested in statistics and coding, I highly recommend you to get acquainted with the environment of our project. It's very, to my opinion, user-friendly environment. It's with the cool community in internet, which might be helpful in solving technical problems or questions during a statistical work. But still, so here, what do we have? We have these 3 lines of code, and you have the output, which tells you which is the correlation coefficient, which is the confidence interval for correlation coefficient, and which is the p-value of correlation coefficient. Yes, so pretty easy. But we need to go this way, hard way. So let's begin. Here's I leave the resource, the link on another resource. There is the channel StatQuest by the genetics and biology, who have very good explanations for statistical topics. Sometimes I borrow the material from their lectures. This is why I leave the link below. This is the formula. How can we calculate the correlation coefficient? For this, we need to know the covariance between x and y, and we need to know the variance of x and the variance of y. So let's begin with the easiest part, variance. Variance, because variance we have discussed earlier in the topic of average values. So let's go through this. So variance is a squared deviation from the mean. Yes, so variance for value x will be calculated as sum of differences between each observation and its squared. This should be symbol of square. And the mean, so we need to square this difference and divide it by number of observation minus 1. Yes, so our data set x is 1, 2, 3, 4, 5, mean value will be 3, and the variance will be equal to 3 minus 1 squared, 3 plus 3 minus 2 squared, and so on and so forth. So 4 plus 1 plus 0 plus 1 plus 0 squared divided by 4 will get us 2.5. Yeah. So this is the variance for x. We repeat this procedure for y as well. So, and we get the sum of x variance and sum of y variance. So variance for x will be equal to 2.5 and variance for y will be equal to 3.9. So this is the variance for x and y. So let's begin. Let's continue with the covariance. Covariance is a bit trickier because the formula is a bit more complicated. So to get covariance, we will need to know the mean for x, the mean for y, and to do this math. So we get each observation in the x dataset, subtract it from mean for x, then we get each value from y dataset, subtract it from mean for y dataset, and multiply these two numbers. And after adding up all these multiplications, we need to divide it by number of observation minus 1. In this case, it will be 4. So I will not bother you with these calculations. I hope that you will believe me that when we subtract 1 from 3 and multiply it by 2 minus mean for y, we get 0.6. The same procedure is kind of here. So we multiply it and divided by 4, we get the number of 2.5. So we have all the necessary elements for this formula of correlation coefficient. So we have a covariance, we have variance of x, we have variance for y. So let's do the math. So R, which is the symbol which stands for Pearson correlation coefficient, will be equal to 2.5 divided by square rooted variance of x multiplied by square rooted variance of y, 3.9. In the end, we get the number of 0.8, which is pretty close to the number which we have gotten by R, maybe the same one. if we round it differently. So you might answer, you might ask me a question. Why do we need this difficult math? Why don't we stop with the parameter of covariance? Yes, so covariance is basically the parameter which tells us if there is any interaction between x and y. Yes, so we know already that if the covariance is positive, the relationship is positive. If covariance is negative, the relationship between variables is negative. So it means with increase in one variable, we see the decrease in other one. Why cannot we limit ourselves with covariance? But why do we need to get with this variance, etc., etc.? Why can't we leave the things simple? The answer is also simple. So here is the dataset that we have plotted. Yes, so where we have one axis with the x values and another axis with y values. Yeah, we have calculated that, okay, there was an error. R equals to 0.2 and variation. So I just remind you that variation is 2.5. Yeah. So here are results of our calculations. Variation is 2.5 and R equals to 0.2. And our question is, why cannot we stop on variation? Is it necessary to calculate the correlation coefficient? The answer is yes, we need to calculate correlation coefficient. Why? Because imagine that we have changed the scaling of y-axis and we've made measurements for y value using different scale, and we get the results which are, let's say, 20 times higher. Yes, so x values remain the same, but the scaling of y-axis has changed. Or, okay, they have become 20 times higher than they were initially. We do the same calculations that we have done earlier, and we see that the variation parameter has changed. It was 2.5, and it has become 25. Yeah. So variation has changed. It has changed in 10 times. But does it mean that changing in 10 times in variation results in the kind of stronger relationship between these values? The answer is no. We can see it even visually, that the rough distance between points to the straight line is roughly the same in both cases. The only differences that you can notice may be caused only by the scaling of the plot, and that's it. And our calculation of correlation coefficient confirmed this. It has remained the same. So correlation remains the same, while scaling has changed and variation has changed. So this is why we cannot limit ourselves to variation. Variation is very sensible to scaling of values on both axes. This is why it cannot be used for any conclusions except of the direction of the relationship. And instead we use correlation coefficient to reduce this influence of scaling and to keep this value of outcome between certain ranges, between -1 and +1. This was all for Pearson's correlation coefficient, and I would like to switch briefly to Spearman's correlation coefficient. Why is it important? Because Spearman's correlation coefficient is the correlation coefficient which is widely used, which is supposed to be used in case of non-parametrically distributed data. So for using of Pearson's correlation coefficient, the data need to meet some assumptions. Primarily, it is the parametric distribution of the data which are enrolled to this study. When these assumptions are not met, we need to switch to non-parametric coefficient, which is Spearman's rank correlation coefficient. So, unfortunately, or fortunately, so it's just the fact that in biomedical science, the majority of data, especially in small studies, usually have non-parametric distribution. This is why you need to know a bit more about Spearman's correlation coefficient. So let's say that you have examined 10 people. You have recorded their age and body weight. Yes, so you have person number 1, which has a body age of 22 and body weight of 56, and another person, age of 22, the body weight of 57, etc., etc. And you need to calculate the Spearman's correlation coefficient. So the trick here is that you need to rank these parameters before enrolling to correlation coefficient. So let's begin with a simpler one, body weight. You see it is already ordered from the lowest to the highest. So you assign this body weight observations ranks, yeah? The smallest gets number 1, the highest gets number 10, and so on and so forth. The trickier thing is with age, yes? So you find the lowest value, which is 21 in this case. It is the only observation with the age of 21, so you assign this person with a rank of age of 1. Then you can see that the next lowest age is 22, but there are 2 observations with 22. What should we do in this case? So these 2 numbers will go as the second and the third in a row. And to assign rank correctly, we add up these ranks and divide them and find the mean among these 2 ranks. So 2 and 3 will give us 5 in sum, and divided by a number of ranks. In this case, it will be 2. 5 divided by 2 is 2.5. So we assign these 2 people with a rank of age of 2.5. Repeat the same procedure for all ages. And we have the table with ranks. So body weight ranked and age ranked. What can happen next? Next, you can enroll these ranks into the same procedure as for the Pearson's correlation coefficient. Let me remind you, it is this one. So you calculate covariance, variance 1 and variance 2, and calculate the correlation coefficient. But in this case, I can offer you a shortcut. So what can we do? We can find the rank difference. This shortcut works only for Spearman's correlation coefficient. So we find a difference between ranks. So we subtract one from another, doesn't matter which one from which one, because afterwards, in any case, we will square this difference, which will eliminate the minus value, even if it is present. Yes, so we find the difference between ranks and square it up. After squaring the rank difference, we find the sum of the squared rank differences, which will be 41.5 in this case. And then we just need to apply a simple formula to find the correlation coefficient. You can see the symbol of Greek symbol rho, which is sometimes used for Spearman's correlation coefficient. So rho equals 1 minus 6 sums of squared rank differences divided by n multiplied by n squared minus 1. So just put the numbers instead of these symbols. And here we go, 1 minus 41.5, the number that we've got from the previous calculations. And we know the number of observations is 10. So 10 multiplied by 10 squared minus 1. I do the math, and we get to the number 1 minus 0.25 plus 0.75. So we can assume from these calculations that there is strong correlation between age of people and their body weight. Yes, so with increase of age, and we can expect the increase of body weight. Important caveat. Correlation coefficient, whichever it is, or 1 or 0.75 or 0.2, it doesn't really matter. It doesn't tell us anything about causality. So we don't know if aging leads to increase of body weight, or we don't know either if increasing body weight leads to aging, which is nonsensical, but still, if we take, for example, another example, like not age, but body height, let's say, yeah, we cannot say for sure which is primary source of association, whether body weight leads to body height increase or body height increase leads to body weight increase. We can assume it from other reasoning. We can think logically. What correlation coefficient tells us is the strength of this association. So we don't know what is the primary source of change between, or primary source of association. We just confirm this association and confirm its strength. So we have the correlation coefficient, but it is not the end of the story, because we would like to know if this correlation coefficient happened by chance. What do we mean by this? So we would like to know if we if this finding is random, what would happen if we took another 10 people and do the same measurements. So the calculation of error statistical significance of this correlation coefficient will tell us how likely is that we would get the same results by chance, yeah? So, or how systematic are these results? For this purpose, we need to calculate the error of correlation coefficient, first of all. We have this formula here for which we need to know the correlation coefficient itself and number of observations. So we put the numbers here and get the value of error of 0.23. And afterwards, we need to calculate the value of t for this correlation coefficient. Again, we need to know the correlation coefficient and the value of error. And usually, if the correlation coefficient exceeds by 2 times and more the value of its error, the results are supposed to be statistically significant. In this case, it exceeds its error in 3.2 times. So we can say that statistical significance of this correlation coefficient is very high. So it is very unlikely that the result that we've got happened by chance. So we may be pretty sure, in other words, with the probability of error less than 1%, that there is genuinely an association between aging and body weight, but which is the main driver, we need to clarify using our reasoning. And final word on the statistical significance of this correlation coefficient. Why do we need it, and can we rely on it completely? So the answer for the question, can we rely on it completely? No, we cannot, because it is not an isolated value, and it should be assessed in combination with other parameters, at least with the correlation coefficient itself. So you can see here that there are 3 examples from the same channel that I told you earlier, a StatQuest example of 3 samples with the exact number of correlation coefficient, which equals 0.3 with correlation. But in these 3 examples, p-value for correlation coefficient is, in one case, 0.8, in other words, non-significant at all. And in other example, it is 0.008, which means highly significant. It means that p-value for correlation coefficient depends highly on the sample size. This is the first conclusion that you can draw from this slide. And the second slide, the second conclusion that you can draw from this slide is that p-value just tells you information about how likely to get the same results by chance, but it does not correlate in any way or doesn't tell you anything about the strength of correlation. Yes, so it is different information that you can get from correlation coefficient itself. So just likelihood of getting the same results by chance. And the strength of association is gotten from the correlation coefficient itself. Okay, this is all from my side. See you on practical lessons and have a nice day. Goodbye.